Well, thanks everyone for coming. My name is Santiago from Zeppelin. Over there is Martin giving out free stickers. So if you haven't got yours, just wave and you'll get yours. Thanks. Okay, we're here for a 2-hour workshop. This is basically a very simplified version of the agenda. You will go through some very beautiful slides. Then we will make a live demo on setting up a project with ZeppelinOS. And then we'll share some exercises, some challenges so you can actually test this yourself. So first of all, what's Zeppelin besides the company I work in? Zeppelin, we basically try to build open source infrastructure for developing secure blockchain applications. Some of you may know us for some audits we have performed. We have audited the Augur code. We have recently released the audit of the Solidity compiler also. We audited the Serpent compiler last year. So our main focus is both security and also development tools for building more secure applications. Among our open source projects, perhaps the most well-known is OpenZeppelin. OpenZeppelin has been going around for over 2 years now, and it's the most widely used repository of reusable smart contracts. And it has a very beautiful community built around it. We have over 150 contributors. We're seeing over 7,000 weekly downloads, etc., etc. And basically, OpenZeppelin provides a set of already implemented and ready-to-use contracts, has some canonical implementations for some of the most well-known EIPs, such as ERC20, SN21, etc. And also some mix-ins and some features that you can spice over your own contracts to add functionality, such as ownable, pausable, that kind of stuff. The other project we're working on, which is why we're here today and why I'm wearing this t-shirt, is ZeppelinOS. And yes, you will notice this is an old t-shirt. It has different casing. I'm sorry, Martin.
Actually, you have the old sticker.
Sorry about that. Branding. Basically, ZeppelinOS is a set of tools for building upgradable and secure smart contracts. ZeppelinOS is actually envisioned to be a huge project that will spawn an ecosystem of reusable and secure code. And what we will be showing for you today is what we have released actually last week, which is version 2.0, which is basically a command line tool that allows you to manage your project and manage a set of upgradable smart contracts. And also linking to online code, which we call EVM packages, but a little bit more on that in a second. Anything you want to add? Cool. So let's start with this wonderful quote about what it is like to write a smart contract, a secure smart contract specifically. Well, emphasis is ours, but the idea is that you're setting up a program live in an environment where it can be attacked by anyone. It's public. It's very difficult to implement security in depth because everyone has access to actually querying, to attacking your code. You can't rely on security by obscurity. You shouldn't anyway, but this makes it absolutely impossible because everything is public, and you have the added complication that once you have deployed a smart contract, you cannot change it. This is what we're looking forward to challenge via ZeppelinOS, which is allowing you to upgrade your smart contracts, whether it is for a bug fix, a security patch, or even a new feature that you need to develop. So, without further ado, let's start with upgradeability. The idea for upgradeability starts from a security perspective. That is that we need to be able to patch a smart contract if we discover a bug on it. But it also maps very well to the software development cycle we're very, very used to. So very few companies just go out into production with a finished version of the product. We're used to iterate, to build more and more features on top of it. And smart contracts being part of the systems we develop, we also need them to be able to iterate on them, to build new versions and deploy them. So how do we handle upgradeability? How do we make changes in the code in a platform where our code is immutable, where the code is low? Well, we work using proxy patterns. Before I go on, how many of you know what a proxy is in this context? Very good. How many of you have already used ZeppelinOS? That's very good. How many of you have deployed a project to mainnet using ZeppelinOS? Ah, okay, interesting. We're hoping to change that today. Okay, so I'm going to go a little bit faster over proxy patterns since most of you are aware of them. The idea is that clients do not talk directly to the contract you have actually coded, but they will always interact with the proxy. The way it's going to work is basically the contracts you code, we're going to call them a logic contract. They are only going to hold the implementation, basically the code, the logic that is going to be executed, but they are not going to hold any storage at all. All the storage is going to be kept in a proxy, which is going to delegate all calls to the logic implementation, to the logic contract, sorry. The logic contract is going to tell it what it needs to be executed, and then it changes in storage are going to be performed in the proxy. Under the hood, this is actually accomplished using the delegate call low-level EVM opcode. It's basically a call from a contract to the other, but stating that the context of the call should remain on this contract. So the code executed is here, but any modifications on the storage happen here. The message sender is the one who called the original proxy. Basically, all the information remains as if it were the original foo call in this context. So basically, what we do with ZeppelinOS, we abstract all this complexity from you. And whenever you want to create a new instance of your implementation contract, we ensure that there is one already deployed on chain, and we spin up a new proxy for you to interact with. So how is upgradeability managed? Using this is actually quite simple. We basically deploy a new version, a new separate logic contract, and we upgrade the proxy. We tell the proxy to fetch the implementation from a different address. Under the hood, this is actually very similar to how Solidity libraries work, with the only difference that Solidity libraries have an address hard-coded on where they actually go to fetch the code. Here, the address is kept in storage, so it can be modified by an authorized admin of the proxy. So what this allows is that all clients will still interact with the same smart contract. Basically, the proxy doesn't change address. It's still the same contract. For all clients, they are still talking to exactly the same address. And we also keep the storage. There are no changes to storage. We don't need to manually migrate all the state from one contract to the other. Basically, we don't need to pick up any storage here and move it here, because all storage is stored here. There's absolutely no storage here. And so if a new call comes into the proxy, it's now going to be delegated to the new implementation. It's going to respond with the new code that you have implemented. So far, so good? OK, perfect. Feel free to interrupt, ask questions. We have 2 hours, so we have plenty of time to chat. So what do we need to do for a contract to be able to sit here as an implementation contract? Unfortunately, it's not seamless. There is one minor change that you need to make, and that is removing constructors. So this is how you would typically write a contract. You just define a constructor with any values you would like to initialize. If you're looking forward to working with upgradable contracts, you need to change this into a standard function. By convention, we typically call it initialize. And we provide a contract that you can inherit from, that's an initializer modifier. Basically, all this initializer is doing is ensuring that this function can only be called once. So once the contract has already been initialized, it cannot be reinitialized again. So why do we need to do this? Basically, constructors, if you go into the EVM bytecode, are not part of the contract code. Constructors are actually run on a separate set of bytecode when you deploy the contract. So if you look at this contract, any code for the constructor is actually removed. So we need to keep that code somehow, and the way we do it from the Solidity perspective is we change it into a regular function that can be invoked by the proxy whenever we need to spawn a new proxy. So what's going to happen is when you create a new proxy to an implementation contract, probably the first function you want to call is initialize. That's going to delegate to the actual initialize implementation here and run any initialization logic that you need that was formerly on the constructor, okay? Fortunately, this is pretty much the only change you need to make to a contract to make it upgradable. There are a few minor details as well, but it's unlikely that you will run into them. Any questions so far? Absolutely. So the idea is that the logic contract only keeps the code, okay? It's the actual code that you have written. In this case, it could be, for instance, a wallet contract. And what you want to do is you want to be able to move from one implementation to the other without losing all your state, without losing the storage. So the way we do it is we basically keep storage somewhere else, in this case, the proxy. Two reasons. First, it's expensive. Basically, copying storage, reading storage from one contract and copying into another, it's a very expensive operation. We have actually worked with several migrations of ERC20 tokens, which were not upgradable into their upgradable versions, which means that, yeah, in that case, you need to copy everything manually. Gas costs were in the order of tens of thousands of dollars, which is not very good anytime you want to make an upgrade. And the other thing is that if you are actually setting up a new contract, the address changes. So you will have to contact all your clients and say, hey, you know, from now on, you need to speak to this guy and not to this one. Having a proxy allows you to just distribute this address, and everyone is going to seamlessly speak to it, and they don't need to know, actually, if the underlying code has changed. Cool. Yeah. Okay. This is actually a question that we get very much when we talk about upgradeability. So basically, let's go a few steps back. The big idea of smart contracts is that they're immutable, code is law, we agree upon something, and that cannot be changed. We're basically offering a recipe to remove that, to make them upgradable and changeable. What we're offering here is the mechanism for upgradeability to be able to do it. The piece that it's missing, that we can talk a little bit further down the talk, is about governance, how to decide when and how you upgrade. You could perfectly have a single address, a single account, and you keep the private key in your pocket that can change and modify all the smart contracts on your project. That wouldn't be very fair to your users, if you want to say so. It's a very good way, actually, to bootstrap your project, to start in a developer early mode, early access, whatever it is. But then you'll probably want to switch that privilege of upgrading the contract to something else, to something a bit more decentralized. It could be a multi-sig wallet where different interested parties can actually decide when to upgrade. It could be a full-blown DAO where all users or all token holders of your project, if your project does have a token, can actually vote on when and how to upgrade. It's going to depend actually on how you want to handle the governance of your project. Think about let's say your project has a set of parameters and you want to be able to tune them. And those parameters actually affect how users behave. You want to be very careful on how you decide the governance that's going to modify those parameters. This is exactly the same scenario, but we're talking about the entirety of the code. Yeah. Yeah. That's a very good question, and actually that's part of advanced topics. We'll go into that in a couple of minutes, but the idea is that there is a restricted set of operations you can do with your storage, and that is only appending at the end of it. You cannot add any new variables in the middle. So when you upgrade to a new version, you cannot change completely your contract. You still need to honor the previous storage layout that you had there. It can be a bit tricky. Our tools try to capture most of the errors that you can make, but still it's something that you need to be aware of. And we'll talk more in depth about that in a second. Yeah.
So when you run the initialization function,
Mhm. Yeah. Thing is, you want to initialize your proxy. Every time you deploy a new one, you want to be sure that it's initialized, because you probably want to initialize it with different values. So let's say you have the wallet contract. You will probably end up having just one single implementation of the wallet contract. And let's say you want your users to be able to spin up new wallets. Basically, every user is going to initialize this contract with a different owner. So you have to make sure that every proxy runs its own initialization process. Cool. Any other questions? Okay, cool. So let's talk a bit about EVM packages. The idea of an EVM package is to be able to share code directly on chain. But let's talk a bit about the motivation for this. So this is the diagram we had just a couple of minutes ago. We have a contract, let's say a regular ERC20 token, and we spin up a new proxy for it. Let's say, hey, I have a beautiful project. I want it to have a token. I'm going to deploy an ERC20. Thing is, we can have actually many proxies pointing to the same contract. Yeah, same example as the wallet we were talking a couple of seconds ago. Since all these contracts, all these ERC20s share the same logic, there is no reason why they cannot point to the same implementation contract. Each of these will have their different storage, so they will have a different name, different symbol, different set of balances, users, so they can be entirely different in their storage, but they share the same code, which is the regular code for an ERC20. And something more interesting also is that all these proxies can belong to different people. I mean, even if, let's say that Martin here deployed the logic contract for ERC20, maybe I can spin up a new proxy pointing to it. Any of you can create other proxies. Basically, this contract is public on the blockchain. It is a logic contract. It is immutable. It cannot be changed. So you can safely spin up a new proxy that points to it and delegates all implementation to that. So not only the proxies can belong to different people, as we were saying, but also the implementation contract can be deployed by someone else. We can have someone that actually works on ERC20 implementations. They release an official ERC20. They deploy it on mainnet. So whenever you need a new ERC20, you just create a new proxy that points to it. Moreover, that same guy can find out an issue, a bug, whatever it is on ERC20, and they say, hey, I'm releasing a new version of ERC20. Maybe it's optimized, maybe have a security patch. Feel free to upgrade to it. So then it's up to the owners of the proxies, basically the guys running each of these projects, to decide, hey, you know what, I'm going to upgrade to the new version of ERC20. And the important thing here is that these implementation contracts can be managed by one party that actually works on those implementations, and all these are just consumers of that code. And that code is consumed directly on chain, okay? So this is what we call an EVM package. It's basically a package, as in a set of code that works for a particular purpose, but it's shared directly on chain. So in this case, this example, we could have an EVM package for ERC20. We could have many EVM package for ERC20 by competing parties, by competing developers. We could have EVM packages that target other verticals, you name it. The idea is that once the logic contract is deployed on chain, anyone can actually leverage it and connect to it directly. Indeed, okay, one of the things that we'll be doing today is actually using one of the EVM packages that we have shared, which is OpenZeppelin, the one we were talking about earlier. Any questions so far? Should we get coding? Okay. Yep. Yeah, that they are handled by the same set of developers. Actually, there is an abstraction here that I purposely removed, but these are all contained within a package contract that actually keeps track of all the different versions and all the different contracts that are provided there. So whenever you actually publish an EVM package, and I'm actually going a few steps ahead, what you are doing is you are creating a package contract that it's going to be a registry of all the versions that you have been publishing, And for each version, it has a directory that says, hey, I'm including an ERC20 and an ERC721, whatever it is. Basically, we are replicating the structure of a package manager, if you want to say so, on-chain. Any other questions? Okay. I think we can start. Thank you. Not sure if you want to add anything about different packages and different projects working on that.
No.
Yep.
Just like ERC20, we have SafeMath library.
Yeah.
That we are linking means all the time to smart contract. So is it like means I tried already deployed a library to link my smart contract, but the issue is that we cannot get the events because events cannot be binded at that. Let's say I'm just replacing the library name with the address, which is means the address of already deployed library.
Yeah.
So what can we do? Like, can we solve this issue with this?
There are actually a bunch of things there. First of all, oh yeah, I'm sorry about that. It's basically they're constantly using SafeMath, which is a Solidity library, and basically how they can leverage all this without needing to redeploy SafeMath every time. SafeMath in particular is a very particular Solidity library in that you don't need to link it, actually. Solidity libraries can be a little bit confusing because they can act in two completely separate ways, which is they can actually be inlined within your code, or they can be handled as a separate code that needs to be linked. The way you figure out whether that's going to happen is if your Solidity library has any public functions or not. Okay? This is actually a very, very confusing aspect of the Solidity language. SafeMath, for instance, has all of its functions defined as internal. So what's going to happen is when you include SafeMath within one of your contracts, the compiler is going to bundle all the SafeMath code within your code. So you're going to deploy something that a single contract that already contains all the code from SafeMath and your logic all bundled together, and you have no way to separate them. If you wanted to separate them, you need to come up with a new version of SafeMath that declares all of the functions public instead of internal. What's the trade-off here? That would allow you to deploy a single instance of SafeMath and then link to it from all the contracts you deploy. But that also means that every call that you make to a SafeMath library is going to have an additional gas cost due to calling from your contract to SafeMath. Due to the nature of SafeMath operations, you typically don't want that. You usually want to separate library code when it's actually going to be big chunks of code that you don't want to be repeating and redeploying every time, and especially that you are not calling that often. And going back to managing libraries with ZeppelinOS, as of now, we are not allowing packages to share libraries. We're only allowing them to share contracts, but that's probably coming in a very, very near release. Yep.
So you're showing delegates of proxies to the
Yep.
package. Now, there's really no difference, but if you wanted to use that package directly and interface it with it directly so that it actually does manage its own memory, does your package manager have you distinguish between those two use cases at all, or is it simply
No.
the eye of the beholder how you use it?
The idea is that we promote not to use the logic contract directly because that's basically using contracts the old way. If you want to do that, if you want to send a transaction directly to the logic contract, at the moment we cannot prevent you from doing so. There are ways at the EVM level that's possible. Currently we don't have access to them. But yeah, basically if you want to interact directly with the logic contract, you can. Just keep in mind that it's going to be an old style contract. You won't be able to upgrade them down the road. And something else is that if you do modify the storage of the logic contract, that has no impact whatsoever on the storage of the proxies. So it's not actually a way of attack. Yeah.
Regarding storage variables, however, that variables that are declared constant, like private constant, like handled differently.
Yeah.
So generally,
Sure. Yeah, private constant functions are not kept in storage. They're just in line whenever they're used by the compiler.
we just use that in the logic contract.
Oh, yeah, absolutely. you should be free to use constant variables without any issues. You only have to be careful with non-constant state variables. We good? Okay, cool. Thank you. Okay, so let's get started. Can you see the screen more or less? Yeah. Yeah, just a little bit actually. Might be a bit too much. Yeah. Okay, so what we have here is a small repo. We are going to share the URL with you a couple of minutes. Basically, the idea here is that we have a wallet contract. It's a standard wallet, as we were seeing a couple of minutes ago. It just has an owner, and it can transfer ERC20 from... Basically, it can store ERC20 on your behalf and then transfer it back to the owner. It's not very interesting. It's just for demo purposes. So what we are going to do is we're going to modify this contract to actually be upgradable. We're going to deploy it with ZeppelinOS. We're going to link it to Open Zeppelin EVM package. We're going to upgrade it, and we're going to play a little bit with it. And yes, this contract has a handful of issues. The idea is that we are going to fix them down the road. Please don't spoil it if you have already spotted them. More zoom? Yeah. Okay, perfect. So, a bit more zoom. Sorry, a bit more zoom here as well. Okay, great. So first of all, let me start the Ganache instance. We're going to use Ganache for the entire testing, so it's actually a bit faster. What we're going to do first is we're going to modify the wallet contract so it's actually upgradable. Okay, this is basically the same transformation as we were seeing a couple of minutes ago. We're going to flag it as initializable, and we're going to change the constructor into an initialize function with an initializer decorator. Okay, let me actually just copy this address, and of course we need to import the initializable contract. We're providing this contract as part of the ZeppelinOS lib package. It gets installed when you also install the ZeppelinOS CLI. And basically this is probably the most interesting contract for you when you're developing your application. You want to extend from this initializable trait that's going to add to allow you to use this modifier to write initializer functions, okay? So basically this is the only change you actually need to do to a code like this if you want it to be upgradable. So let's make sure it's compiling. Cool. So we're going to init a new ZeppelinOS project. Let me actually clean up a few things. Sorry, I have been running some last minute tests, of course. Actually, so last minute that I haven't even committed everything. Sorry about that. So let's create a new ZeppelinOS project. Let's call it My Wallet, for instance. So this is now going to tell ZeppelinOS that, okay, we want to start using this as a ZeppelinOS project. You will notice a few JSON artifacts that are used by ZeppelinOS. For now, it's just this file, zeppelinoS.json. It doesn't have many interesting information for now. But what we're going to do first is we're going to tell ZeppelinOS to actually track all the wallet contract we have just written. So we're going to run an add operation. Cool. So now ZeppelinOS knows that wallet is part of our upgradable project, okay? So what we want to do now is to actually get this contract on chain. So what we're going to do is we're going to tell ZeppelinOS that we want to work on the local network. We're going to start a new session. This is actually not required. It's just so that ZeppelinOS remembers that all operations from now on are going to be carried on a particular network. Otherwise, you would need to repeat, I want to work on the local network on every command, which is a little bit of a hassle. Let me grab one of the addresses we have here. And we want it to expire in a day or so. Okay, so now we're ready to actually push our contract to the network. Okay, so what's happening here? ZeppelinOS has actually taken our wallet contract and has deployed one instance of it as a logic contract. Okay, so now we can start spawning new proxies that point to it. If we go back to the diagram we had, what we have just done is deploying this logic implementation contract. Okay, so anytime we run a push operation, that's going to upload that contract on the blockchain. Okay, so now we should be able to create a new wallet contract, and we want actually to initialize it using an address as an argument. Let's go with this guy, for instance. Okay, so what has just happened here is we have created a new proxy that points to this wallet contract. But we actually want to do something with this, right? I mean, the wallet only works with ERC20 tokens, so we want to somehow be able to create now in order to start playing in our local network with our new wallet. So what we're going to do is we're going to link OpenZeppelin ETH. And actually, let me stop here for a second. I have told about you a bit earlier about OpenZeppelin, which is a set of reusable smart contracts that we help maintain. Why am I using OpenZeppelin ETH and not the vanilla version of OpenZeppelin? So, due to this requirement we have that all constructors need to be changed into initializers, we are maintaining a fork of OpenZeppelin called OpenZeppelin ETH that has all contracts already set up for being used in an upgradable environment. They all extend from initializable and have initializer functions. What does this mean for you? If you are actually writing contracts that you want to be upgradable, you should not be using the vanilla version of OpenZeppelin. You should be using OpenZeppelin ETH. Okay? That's one of the changes it has. The other one is that it actually already provides some pre-deployed contracts on chain, such as an ERC20 token, which is what we're going to use actually right now. And something else on this, we don't plan this to be like this forever. We are working on automating the process of making a contract upgradable, which is automating the process of changing constructors into initializers and a few other tweaks. So later down the road, you won't need to make any changes, and we won't need to maintain separate versions of OpenZeppelin for guys who work with constructors and guys who work with initializers. It should all be handled directly as a build step. So, yeah.
Just to make sure I get this initializer. So what just happened was you created a logic contract, and then from the logic contract you called it init the initializer, and so the logic contract created its own proxy.
No, we have created the proxy separately and told the proxy to point to that particular logic contract.
You haven't called the initializer function yet.
Yes, we have. Actually, this instruction takes care of everything. This instruction is going to create a new wallet instance. It's going to initialize using this address as an argument. Remember that, sorry, it should have stopped a bit more there. The wallet initializer takes an address that's going to be the owner, so we need to provide this parameter when initializing the new proxy. This is this value here. So the CLI is going to tell you that it creates a new proxy to a logic contract. This is actually the address where the logic implementation of the wallet is sitting. And it's initializing it by calling the initialize method using this parameter that we have supplied as an argument, in particular as the owner. And it has created a new instance at this address. So if we want to actually interact with the wallet we have just created, we need to talk to this address in particular. And that address is never going to change, even if we change the underlying code. Cool. Yep.
Is the only way that, so it has all of the information that it needs to know about what storage it cares about just from that initialize modifier? That's what's telling.
Sorry, not sure if I followed.
How is when you actually create the proxy,
Yeah.
it knowing what storage it needs to care about?
That's the beauty of it. It doesn't need to know. The proxy doesn't need any information on the storage layout at all. And how does this happen? let me show you. For instance, if you write this line in Solidity, down the road, it's going to be compiled as store this value, the owner, in slot 1 of the storage. So the proxy doesn't even know that it's actually holding state for an owner, an address, a uint, or whatever it is. The proxy only executes commands that he reads from the logic contracts. One of those commands might be store this particular value in slot 1. And the proxy is going to execute that.
So just the fact that you're using delegate call takes care of
Everything, absolutely. The code of the proxy only has basically a big chunk for making the delegate call to the logic implementation and some access control for who can change the address of the logic contract. It's basically a very, very simple contract that performs delegate calls and can be, its implementation address can be updated. And it also keeps track of the owner. Yeah.
So are all implementation, like all proxies, the code of proxies are all the same?
All exactly the same. Yeah.
Just to clarify that command ZOS create wallet.
Yep.
So it's using the previously deployed wallet contract.
Yeah.
And so that means everything in ZeppelinOS is proxy by default then.
Yeah. Exactly. We did have a command actually for creating non-upgradable contracts. It has been deprecated at the moment. Actually, no one used it. And if we see reason to reinstate it, we may, but truth is, yeah, we make everything upgradable by default. And actually, if let's say you create a new wallet, actually, we can create a new one. Let's pick another guy here. Oops, sorry. If I create a new wallet, what you will see is that the logic contract address being used is exactly the same as before. So what we have now are 2 proxies pointing to the same implementation contract. So creating a new instance of your wallet doesn't require you to deploy all the logic contract again. You only need to deploy a very thin proxy that points to it. So this also helps a lot in saving gas when you need to deploy several instances of the same code. And furthermore, if wallet was provided by an EVM package, you didn't even have to pay the code for uploading the logic contract. You only paid for creating the new proxy. Okay? Okay, so let's move forward with linking OpenZeppelin. Sorry, the no install flag is so that it speeds up a little bit. Otherwise, it would actually grab the package, install it, and want this to be a little bit faster. So what we're doing here is we're instructing ZeppelinOS that, okay, now we want to be able to use code from OpenZeppelin ETH. What this is going to enable us is to actually create proxies to the logic contracts that have already been deployed by the OpenZeppelin ETH team. However, those contracts were deployed on Mainnet, Kovan, Ropsten, Rinkeby, but of course, not in the ganache. I have just started 5 minutes ago on my computer. To work around that, we provide a function that you should only be used in development mode, which will actually create a copy of the EVM package in your local network as if you were working on mainnet where this is already previously deployed. This is actually going to recreate the same state that is present on mainnet or on testnet on your local ganache or in your local tests. Okay? We need to do this because there is actually no way for us to pre-deploy all contracts in ganache or private networks. So basically what has happened here in a very, very verbose output is it's telling us that it has deployed all of OpenZeppelin ETH in my local computer now. So what this allows me to do is it allows me to create a new standalone ERC20 contract from OpenZeppelin. Okay. And I have to initialize it, and I hope you don't mind, but I'm actually going to copy this information because it takes a handful of parameters. If you see, it takes a name, a symbol, the number of decimals, the initial supply, the initial holder, the minters, the possers, and a few other things, and it's actually much faster if I just copy this information. So we're going to create a new ERC20 token. It's going to be named my token, have a ticker of MYT, 8 decimals, an initial supply of 100 or so tokens, and I actually want the wallet to be the initial holder of the funds. So I'm going to copy the address of the wallet. We have 2 wallets. Let's go with this one. Even the addresses are similar. Okay. Okay, so what we have just done is we have created an ERC20 instance using the code provided by OpenZeppelin-ETH. Again, if this had happened on mainnet or a testnet, we wouldn't have needed to deploy the logic contract. It's already out there, ready to use. And it's safe to use because the logic contracts themselves are immutable. There is no risk for the maintainer to actually changing them. If you want to upgrade into a new version, you have to manually opt in to make that upgrade and actually choose to point your proxies to a new instance of the logic contract. Okay. So we have an ERC20, we have a wallet, we have funds. I think we can actually, let's create, start the Truffle console. Okay, cool. So let's grab our wallet, which was this one. Oops, sorry. This should be our wallet address, and they have an extra comma here. Okay, so we have our wallet. Cool. We have our ERC20 token, which has just been deployed here. Oops, sorry. It's actually a token. So we should be able to query the balance of the token. Sorry, the balance of the wallet. Okay, so far so good. Okay, so we have the proxy for our token, which we are interacting with, the proxy for our wallet. We have everything ready. We can actually call one of the methods of our wallet. We can actually transfer ERC20 tokens. Sorry, I don't actually recall the parameters. Okay, first the token address, then who is going to receive them, and then the amount. Okay, so actually, let's do something first. Let's grab the owner of the wallet, and let's see which accounts we have available, and we will work with this fella. So this is going to be someone. A very descriptive name, of course. Okay, so what we can do now is we can request a transfer of funds from our tokens to someone for, I don't know, 1,000 tokens. It's not much, it has 8 decimals. And we're going to have the owner request a transfer. Okay, so transaction goes through, we're in Ganache, so everything is super fast. And we can check the balance of someone, which, yeah, the guy has received some tokens. What problem do we have now? We have no access control in our wallet, so actually someone can decide to invoke the transfer ERC20 function as many times as they want. If we go back to our code, we see indeed that transfer ERC20 can be called by anyone. Okay, so good thing that I forgot to add this. So we can actually fix our contract now and add this check. So we are going to require that message sender is actually the owner. What we're going to do is we're going to upload this new logic contract to the blockchain. It's going to compile. It's validating that everything is okay, and it's actually uploading the new version. So now what we can do is we can actually instruct ZeppelinOS to update the proxies. So what has just happened now with the push operation is we have uploaded the new logic contract, okay? But just realizing that you cannot see anything at the bottom. Why haven't you told me? Let me actually move this. Is that better? Maybe? Okay, cool. So what we have just done here is we have instructed ZeppelinOS to upload the new logic contract on chain. Okay, so now we have 2 different copies of the wallet contract, one with the bug, one with the fix, so that only the owner can manage them. both of our proxies are still pointing to the old version. So if we want to update them to the new version of the wallet, we just need to run an update command, and this is actually going to change the address for all of the proxies. Not sure if you can actually see, but what this is telling us is that it's actually upgrading a proxy to the logic contract. This is the new address of the logic contract, and these are the addresses of the updated proxies. So what does this mean? That if we keep interacting with the same wallet contract, we should not be able to perform a transaction from a non-owner address. And let's see if it works. Yeah, we're actually getting a revert here, and if we try to make it from the owner, it's actually working. So note that at no point I have actually changed what the wallet instance is in the Stratford console. We're still pointing to the very same address in our local Ganache instance. So what this means is that transparently for the client, for ourselves who are working in this console, the underlying code has actually changed, and we didn't have to modify anything in our end, in the client's end. Okay? So, any questions so far? Yeah.
Have the balance changed?
It shouldn't have. Of the wallet, well, we have performed, I think, 3 transfers, right? So, yeah.
So we keep the state.
We have kept the state.
Wow.
Actually, this is actually the state from the token, and we haven't updated the token. If we do want to check that we have kept the state, we can check the actual state of the wallet, and yes, it hasn't changed. Thank you so much for your question, fellow stranger. Yeah.
The point where you would basically have to ask all your community members would be before saying ZOS update.
Yeah.
Right? Okay.
Exactly.
And then what happens after you update it if you now interact with the old proxy contract?
If you now, sorry?
If you're now interacting with the old proxy contract.
Basically, all the client code that is interacting with the proxy contracts doesn't need to know that anything has changed unless you have added a breaking change to your ABI. Basically, if you have changed the public interface of your contracts, then yes, you need to notify your clients that we are working with a different public interface. If you have only changed the implementation, then no, you don't need to warn them at all.
I was confused actually. I was wondering about the old logic contract, but you can't really interact with that because it doesn't have storage, so
Exactly.
it doesn't make sense to interact with it.
Yeah, the clients never hear about the logic contract at all. They don't. Actually, one of your clients shouldn't even know that it's interacting with the proxy. And they should have no indications at all that the contract they talk to is a proxy, because the proxy doesn't yield any information differently than the logic contract. The only actual difference that you'll have is a very, very small gas surcharge due to the delayed call from the proxy to implementation. That's the only noticeable difference.
How are you managing when you need to modify the structure storage?
Thank you. Let's go for an example then. Actually, if you go into README, that I'm going to share this with you in just a second, we have a set of challenges near the end for you to try and implement. And one of them is to actually add more people who can play around with the contract, okay? So let's say that we add, I don't know, a mapping from address to a flag, whether they can manage funds, okay? So we'll check whether message sender is the owner or whether, the message sender can manage funds, okay? Missing a parenthesis there. Okay, so let's say I want to add this feature, so I have added this particular variable in storage. If I try to now push this new implementation, what's going to happen is that the ZeppelinOS is going to complain that you have modified the storage layout in a non-compatible way. Why? What has happened here under the hoods? And I can happily go into the advanced topic section. So, can I get there? Thank you. I like scrolling. So, let's say we have a regular contract, okay? We have defined 2 fields here. What's going to happen under the hood is that Solidity is going to assign each of these state variables to a particular slot in storage, okay? So let's say we initialize those values with, I don't know, 42 for value because 42 is a beautiful number, and owner as any particular address. If we then modify our contract with a new version and add a variable in the middle, what's going to happen is the compiler is going to run again, and it's going to assign, once again, the slots in the order in which the variables are declared. This means that after you perform the upgrade, the proxy is going to read from its own storage. For flag, it's going to read the 42, for value, the address, and owner will be moved to 0. So you would not be preserving your storage semantically. I mean, the storage will be kept, as in the slots will be the same, but you would not be referring to the same thing when you talk about your value. Your value will be actually moved down a slot and will actually pick up a different value from the previous version of the contract. So the way to work around this is always define new variables at the very end. Basically, that's what the CLI is going to check. There is a small detail here, and that is that here we're talking about just a single contract. What happens if you have inheritance? You have multiple inheritance. What's happening there is Solidity under the hood linearizes all your contracts. So basically, even if you have multiple inheritance, you have a complete chaos of ancestors. You have some incest going around, whatever it is. What's going to happen is Solidity is going to end up with a linear sequence of your contracts. It's going to walk each of these contracts in order, and it's going to look for all the variables declared in that order, and it's going to map them into the particular slots. So you need to be careful when you upgrade, not only in what storage variables you're adding, but also what storage variables the contracts you inherit from are adding. The CLI is also going to check that for you, but still you need to be very aware of it. And that's also a reason why, if you look deep into the code of OpenZeppelin.eth, you'll notice that at the very end of every contract, we add a gap. Basically, we add a set of unused variable slots in case we want to add new functionality later down the road and we need new storage variables. Yeah, he was first, sorry. Yep. Sorry, I forgot to mention that. OpenZeppelin is open source, ZeppelinOS is open source. Pretty much everything we do is open source. We love open source. We have a lot of contributors in OpenZeppelin. We have more people jumping into ZeppelinOS. You are welcome to contribute. Yeah, everything ZeppelinOS related is on the ZeppelinOS repo. We're going to share it near the end. But yeah, absolutely everything is open source.
Included the development process.
Yeah, it makes sense that it came from microphone. Okay. Yeah. Solidity code. Yeah. First answer. It's not specified. We reached out to Chris and Alex from the Solidity, but they are basically the two main maintainers of the Solidity compiler, and they have guaranteed that this is not going to change in the foreseeable future. We are extracting this information from the AST of the contract at the moment, and we're also working from actually extracting this information from the compiler itself, rather than having us derive it from the AST. But the compiler does have all these mappings stored internally. We actually have a pending pull request to have it actually output that explicit information so we can leverage it and double check it. But yeah, during version 4, version 5, and most likely version 6, layout is not going to change. We have checked with them and we can be sure of that. But yeah, it's a very good observation. The end? Yeah. Yeah, also a very good question. When you have a mapping, what's actually going under the hood is that every element gets stored in a storage position that is the hash of the key plus the slot of the mapping. What does this mean? It means that since keys will be the same because you want the same information to be stored, that's not going to change. The only thing that can potentially change is the slot that the mapping is assigned. So if value were a mapping instead of an integer, everything in this mapping would get stored in a position that is the hash of 1 plus the key in that mapping. So in that case, you have to, basically you need to look after exactly the same as you're looking with any other kind of variable. Only add new mappings at the very end. For structs, it's actually the same as if they were little contracts. You have to make sure that you're only adding new information on the structs at the very end, and you need to be careful with tightly coupled struct arrays. That would be the only problem you would have. Yeah. Yeah, it's a very good question. We have a separate repository called Labs where we explore different alternatives. And one of the options we had explored is, okay, so instead of having the proxy have a single implementation address, to have one address for each public function it has. So we would have one logic contract for each of the public functions we would work with, and the proxy would act like a, say, virtual dispatch table. It's going to move, basically check out which call it had. Let's say foo got called. So the proxy would see, okay, which address do I need to call to answer to foo? It's going to route to a different contract, and that would allow you to just modify the foo function. We eventually decided not to go on that route because it has much increased costs in gas. Basically, the initial deployment is much more expensive. It's more costly to deploy two small contracts than a big one that does the same. And also, basically, all the logic here for the dispatch would also increase gas on every call. And also, it makes code reusing between the functions much more difficult because any private helpers, let's say you have in your contract, need to be duplicated in every of them. It's also more difficult to maintain consistency among them. So we eventually dropped that approach in favor of redeploying the entirety of the contract. That said, your contract could use, for instance, Solidity libraries. They would be deployed separately, and you could actually keep linking to them and not changing the libraries, but yes, your contract, or vice versa. But yeah, you have to make that explicit. I completely forgot who's going. Let's go with you. Yeah. We're getting all the best questions today. Love it. This is what's going to happen. So let's say that if you go here, you end up with a self-destruct to the owner, right? And actually, let's remove this so we don't get the error we had. And okay, let's push. There. The CLI is not going to allow you to do it because, yes, it's a potential error. If someone calls directly into the logic contract and destroys it, what's going to happen is all the proxies will become orphan and will be delegating all the calls to nowhere. Basically, all your proxies will become frozen. If you're interested, that's what happened with one of the versions of the Parity wallets. Yeah. Yeah. Not going, sorry? Yeah, question is, what was the reason for not going with the eternal storage approach? Eternal storage is basically an approach in which the storage for the contracts cannot be modified, ever. It's actually a very safe way for not screwing up with storage layout. It's also very limiting. We had originally designed eternal storage because the proxies were actually aware of the storage layout of the contract they were delegating to. So we did spin different proxies based on the contract logic that we were working with, which is actually one of the very first questions we got today. Eventually, we realized we didn't need to do that. The proxies didn't need to be aware of the storage layout of the implementation contracts, and we just dropped that restriction in favor of some additional checks while you are deploying a new version of your contracts. But yeah, basically, eternal storage is much less flexible because the idea is that you don't modify your storage at all. Sorry, you don't modify the storage layout. Of course, the value of the variables can keep changing. Yeah.
So if you have a proxy which has a different logic contract for each function, then how would your storage be laid out?
The storage is always kept within the proxy, but you need all of your logic contracts to inherit from a base contract that defines the entirety of the storage that you will be working with. And none of the little function contracts can define any additional storage. Otherwise, you'd get a clash. Very good observation, yeah. Again, this is all on the labs repo if you're interested. We decided not to go that way eventually due to all these complications. And, yeah.
You said that in each your contract you usually add special slots for future upgrades. Could you show how it's
Yeah, absolutely. Thank you. Let's see if the internet gods are smiling down to me today. Yay. Okay, so this is Zeppelin ETH, basically the dependency we're pulling. Let's go with, I don't know, ERC20 possible. So this is basically a behavior for ERC20 to make them possible. This is what we're doing. As simple as that. And something very important is that this doesn't cause an increased gas cost. It's just a declaration that Solidity is going to pick up and it's going to say, hey, these 50 slots are reserved for gap, so I'm not going to use them. And nowhere in the contract we write there, so it actually makes no difference at all in compile time, only that it pushes all subsequent slots down. So if later down the road we need to add a new state variable here, we just change this 50 into a 49, and we're safe to add a storage variable here, knowing that we will not be stepping over any of the storage slots of any children of this contract. Make sense?
Yes.
Cool. Yep.
And it doesn't matter if the variable you're making is uint or it can be a string or anything.
You should not be changing the type of your variables. Oh, sorry, you mean here on the gap? Yeah, I think it shouldn't matter. We use uint because it's more explicit as to the size we're reserving. Yeah. Yeah, I think string shouldn't make a difference.
One of the problems that I'm seeing is how are you managing, like, do you want to imagine that you have two different smart contracts?
Yeah.
They are upgradable, both, and you want to, and you have one, the first contract for the second contract.
Yeah.
So you make the deleted code, which makes another deleted code, but then I guess you would be using the first storage.
Yeah, thing is, if one of the contracts is making a delayed call to the other, it's because it wants to do it with the storage of the first. So let's go one step backwards. In which scenario are you thinking about a contract making a delayed call to another that is not a proxy or a library usage?
I'm the proxy, so I have one contract which is using a proxy.
Yeah.
It's calling another contract, so it's calling to the proxy, to the other contract.
See what you mean. That's not going to be a delayed call. That's going to be a regular call at the Solidity level. So if you make a standard call, let's say, for instance, here the wallet contract has a reference to the token contract, and it's calling transfer into it. Okay? So this is actually translated not as a delayed call, but as a regular call. So it's going to affect the storage of the recipient of the call, which is the proxy of the token. So what's actually happening here, I have a whiteboard. Okay, tell me if you actually see anything. Can I get that? Thanks. So basically what's happening here is you have your wallet proxy. Oh, I have a horrible handwriting, by the way, sorry about that. You have the wallet proxy that actually makes a delayed call to the wallet implementation. And this guy is going to make a regular call to the token proxy, which is actually making a delayed call to the token implementation. So what happens here is you talk to the wallet, you say, okay, can you please transfer ERC20? The wallet proxy delegates that call to the implementation. That implementation reads, hey, make a call to the token proxy. And actually, the address for this guy is actually stored here because it's part of the storage of the contract. And this proxy is then making the delegate call over onto the token implementation. The trick here is that this one is a regular call and not a delegate call. And if you're interested in going even deeper down the rabbit hole, there is a limitation right now that these proxies cannot be nested. I mean, you cannot have one proxy delegate call into a second proxy that delegates call into yet another. We have plans for actually fixing that, but right now it's a limitation that you might run into. Yeah.
This is not too off topic. I'm just curious how you guys integrate migrations. Because let's say, for example, you have a smart contract and you want to add a reference to another smart contract.
Yep.
So you need to update the logic to include that field and then set that field, for example, by the owner. So do you guys work with truffle migrations or?
No, we do not work with truffle migrations. What we do is we encourage users to add an upgrade method. Let's say that you want to add an address to something else. So you request the address to that something else. You require that it hasn't been set previously. Sorry. And you actually assign it. And what we do is we provide, let me see if everything's reasonable. Yeah, let me remove the self-destruct. Okay, so what we're doing is we provide from the update command. Sorry, let me actually expand this. Using the update command, you have an option to actually run an upgrade function atomically. So you can upgrade your contract into a new version and at the same time run a migration function. And that's going to be taken care when you actually run the update process. So I can actually push. Let me make this one public. I'm sorry, I'm going to have to push again. Okay, so I should update our wallet contract. We are using a method name upgrade. And we are using as argument, let's pick any other random address. I like this one. Okay. Sorry, I actually need to spin up a new console. This difference is because Truffle loads the ABI of a contract when you actually spin up the console, so if you add new public functions, you don't have access to them unless you reset. So let's pick up this guy and ask for something. Sorry, my bad. Okay, there it is. So what we're doing is, this is actually the same address we used as an argument when upgrading the proxy to a different version. So as you can run initializer functions when updating, and you can also run migration functions when updating from the CLI. Yeah?
So are those stored in that JSON file, network-specific JSON file, so it's sort of tracking what's happening already?
I can show you the network-specific JSON file. Sorry. It's a little bit extensive, but yeah, it keeps track of pretty much everything that has been going on. Actually, I can show it here. So this actually keeps track of, this is the contract information. So what we keep track is the address for every proxy, the version of the project. You can actually bump your project and have different versions, and the implementation address. We don't store which arguments we have used for running each of the migrations. We only keep for every proxy, which is the implementation contract. basically nothing prevents you from actually updating the proxy and then running the migration separately on your own.
So we have to track that ourselves.
Yeah. But it's actually a very good idea. Do you have anything for taking feedback? Let me hold that for you. Okay. Had another question over here. Yeah. I see what you mean. Yeah. So the question is how to handle two instances of the same smart contract, which is a problem nowadays on Truffle. So basically, the way we do that is when you're updating a new when you're updating a contract, you can either use the name of the contract, in this case would be wallet, that would update all wallet instances you have, or you can refer to it by address. You can actually paste in the address of the specific proxy that you want to upgrade, and ZeppelinOS is going to check that it's one of your proxies, that you do have access to it, and to what it needs to be upgraded. And in that case, you can choose to upgrade one contract, but not the other. Or you can actually run different migrations for them. For instance, you could update one of your wallet contracts using, I don't know, one argument, and then use a different argument for your other wallet. It depends on whether the migration should be the same for all of them or should be particular for each of your instances. And no, we don't provide any automated way for tracking this. That's something that we leave you on your own for doing it. Yeah. That's actually a very good question. Question is whether he can customize the upgrade process to give, for instance, a 10-day warning period for the upgrade, which is a common practice. The update command is going to perform the upgrade. It's not going to do anything else. At the moment, we are not providing any off-the-shelf governance solutions. What we do is we allow you to basically transfer the ownership of the proxy to something else. One of the commands we have is setadmin. So what this command is going to allow you to do is, for a particular proxy, it basically relinquishes your ownership for upgrading to a different contract. We have a blog post explaining on how to do this, for instance, for transferring ownership to a multi-sig. So you need a different set of addresses to actually approve the upgrade process before it goes through this. What's the trick here? If you do this, you can no longer manage this proxy using the ZeppelinOS CLI. You need to do it on your own. We're working for providing some off-the-shelf solutions that will also integrate well with the CLI. At the moment, its ownership is single address, and you have to work it manually if you want a different solution. I'm sorry? Yeah, the proxy contract is provided as one of it's bundled within ZeppelinOS, yeah. No, we're not providing any way for customizing it. My lazy answer would be it's open source. Feel free to fork it and change it. Anyway, I'm curious if you want to tell us later what would be the changes that you would be making to the proxy contract. I'm not sure if we're firing them on the proxy itself, but on the contract that manages the proxy upgradeability. To be honest, I'll have to double check. Yep.
If I have two contracts, contract A and contract B,
Yeah.
which both have some variables, and I want to add a variable to contract B, then I would have to append it to the variables in contract A to make it work because of
You mean in the case where A extends from B, right?
Yes.
Okay, so question is you have two contracts, one extends from the other. You want to add a variable to the parent contract, how you handle it. That's why we have this little trick here. If you want to add it on the parent contract, you need the parent contract to have previously reserved some free space to actually be able to do it. Otherwise, no, you have no way to do it.
So I would then have to decrement that to 49?
Exactly. You only need to do this on your base contract in case you anticipate that you would need to actually add new storage to them.
And then put it below the gap?
No, put it over the gap, actually. It's going to be the same. It's all reserved space you already have. Yeah.
Can I use some specific compiler version? Like if it's 2.0 in ZeppelinOS, we're using 0.25.
We're using 424, but yeah, honestly, I see no reason why you cannot use a different version. Where at the moment we integrate with Truffle for both for connecting to a network and for managing the compilation process. You should be able to update to a newer Truffle version that works with a newer version of the compiler and work with a new one as well. Yeah.
But in Truffle beta version, as of now, in Truffle beta version, they have provided a way to compile your contract with some specific compiler version.
Yeah, I think that you can provide that information on the Truffle configuration file, right?
Yeah.
Okay, so we're basically delegating all that to Truffle. Actually, let me go back to the project for a second. The project does have a Truffle config. It requires a Truffle config. So you could add here all the compiler information you need, and it should be picked up by Truffle.
Okay, but your smart contracts will be in the different version.
Yeah, they are tagged with the Pragma 424. We haven't upgraded them yet to version 5 or Solidity. But it's actually a very good point. Yeah, we should look into that. Any other questions? Okay. So, let's see. Okay, so what's going to happen now is I want to share with you a few more thoughts and then leave you to the challenges in case you want to start hacking here. We'll share this repo with you now, or if you want to go have lunch, which is totally understandable. Let me go back to the slides for a second. The last thing I wanted to talk to you about, switch layout. No, I have one here, thanks. So this is quite an advanced topic, but few people are aware of this. We have so far been interacting with ZeppelinOS via its command line interface, which allows us to basically, from bash, throw commands at it, which will create new proxies, upgrade new versions, etc., etc. The ZeppelinOS architecture is actually quite more complex than this. You can actually speak with ZeppelinOS at different levels of abstraction depending on how you want to work with it. By far, the easiest version is just using the bash, the command line interface. But you can also interact with the CLI using directly JavaScript. Basically, for every command, there is a direct JavaScript function that also that performs exactly the same actions. So if you have a build script already written in JavaScript, you can actually speak with the CLI, with the command line interface directly at the JavaScript level. And a little bit lower, we have the ZeppelinOS library functions. We expose an abstraction that it's a project. Basically, for us, a ZeppelinOS project is what we have just been doing here, a set of logic contracts with their respective proxies. And this object is going to expose similar functions to the one we have been seeing previously. The difference here is that this guy is not going to keep track of all the project information in JSON files. It's not going to provide a handling command line interface, etc. This is just a library that is consumed from the command line, but you can still use it directly. And if you want to go into an even lower level, we're providing abstractions also directly for the smart contracts we're working with. So you can speak directly with the proxy and ask to deploy a new instance without having some abstraction on top of it, tracking, okay, how many you have created, where are the logic contracts, etc. This is basically the lowest level you can go. But the idea, basically what I want to share with you here is that if you already have a deployment script, a set of tools, or whatever it is, where this doesn't fit, you can actually look into other levels of abstraction for integrating ZeppelinOS into your project. If you're starting a new one, I would suggest going with Bash. But if you already have some sort of script already present, you might want to take a look at any of these options. Okay, so it's hacking time for you. There you will find the GitHub repository, which we have been working with. There is a lot of challenges in the README in case you want to tackle them. And there is step-by-step instructions detailing everything we have been doing so far in case you want to reproduce them on your own computers. And I guess we'll be here for about another half an hour. Feel free to ask questions. We'll be walking around. And, well, we'll be here if you need anything. Yeah, questions?
Yes, could you go back one slide?
I don't think so. That's this one, right? This one?
No, the last one talked about the bash and the...
This one? Okay.
So what if you have JavaScript tests, profit tests?
Yeah.
How would you, which one would you use to, only just do artifacts required and then convert to...
Got it. At this level, at the command line interface level, it exposes, if you include the ZeppelinOS CLI in your project, you'll have access to a function that is a test project, which is going to go through your ZeppelinOS JSON files. It's going to understand the structure of your project. It's going to automatically deploy it on Ganache on every test you have.
Okay.
So basically, you just have to make a small before each setup in which you create everything, and then you can speak to the project and ask it to create new proxies for you directly from your tests. Or you can test in the old way and speaking directly to your contracts. Again, you should see no difference except for a slight gas increase on every call. Any other questions? Okay, so feel free to get hacking and we'll be around for any questions. Thanks.